All right, so we're in section 3.9 now, and we're talking about related rates. And related rates are one of the major applications of derivatives that we look at. This particular section is not going to be terribly explanation heavy as far as it is example heavy. That's just the way that this is taught. So the idea here, given this little mini paragraph at the top, is that in a lot of applications that you would be using calculus in, you're working with formulas of some kind. You're going to see that we use a lot of geometry in this section, so there's a lot of area, perimeter, volume, surface area formulas and things like that. It's not all restricted to geometry, but that's just a common example. We have multiple quantities that are related to each other. So for example, the area of a circle is directly related to its radius. Area is equal to pi r squared if we're talking about a circle. So if you have two or more variables that are related to each other in an application, and if one of those variables is increasing or decreasing with time, as time passes, then that's going to cause all of those related variables to change with it. And so associated with each of those variables is a rate of change with respect to time. And that's where you get these rates that end up being related to each other as well, hence the name related rates. It's difficult to wrap your mind around this without looking at a bunch of examples to see what it is that I'm talking about. So let's just go right into the examples. We're going to start with a straightforward one. Let's suppose that oil is leaking from a ruptured tanker and it spreads in a circular pattern. If the radius of the spill increases at a constant rate of 2 meters per second, how fast is the area of the spill increasing when the radius is 30 meters? So you have oil, and it's leaking in a circular pattern, and the circle is going to be growing as the oil continues to leak. And the quantities that we're interested in, just by reading through the problem, the dimensions of the circle that we're interested in here are its radius and its area. Okay? So what is the relationship between the area of a circle and its radius? Let's start there. Area, like we said just a minute ago, is pi r squared. Okay? Now, looking at the information that's given to you in the problem, it says the radius of the spill increases at a constant rate of 2 meters per second. So this is a rate, which means it's the derivative of something. Specifically, it's the derivative of the radius of this circle with respect to time. Now, because the radius of the circle is growing, since the circle itself is growing as time passes, you can think of the radius as a function of time. And because the area of the circle is directly related to its radius, the area of the circle is also a function of time. Both of these quantities, A and R, are changing as time passes. So even though there's no t showing up anywhere in this formula, it's sort of implied in this specific application that t, or time, is a variable lurking around in there. So what I'm going to do is differentiate both sides of this equation with respect to t. Okay? On the left side, I would simply get dA dt. And on the right side, we're using implicit differentiation here. You're going to be using implicit differentiation all throughout this section, so it might be worth reviewing that if you feel a little uncertain about your ability to do that. But here I have pi r squared, so the derivative of this would be 2 pi r, but then again, remember, we're technically using the chain rule because I'm not differentiating with respect to r. R is not the independent variable here, t is. So the chain rule would say that I have to multiply by the derivative of the inside function. In this case, the inside function is r. So its derivative would be dr dt. Okay. Now, what information are we given in the problem? And what information are we looking for? So we are told that the radius of the spill increases at a constant rate of 2 meters per second. It's the radius that's increasing at that rate. That's dr dt that we're talking about. So this quantity right here is equal to 2, according to what we're told. We're also told that we want to know, or we're asked to find the area specifically how fast the area of the spill is increasing when the radius is 30 meters. So even though the radius is growing, we are interested in the moment in time when the radius is exactly 30 meters. So that indicates that we're going to be using a 30 for R here. Finally, the question is asking how fast the area of the spill is increasing when the radius is 30 meters. So how fast indicates that we're looking at a rate of change in our area specifically. We want dA dt. So this is where I plug in the given information. dA dt is equal to 2 pi. The radius, like we said, at the instant in time that we're interested in is 30 meters. So I plug 30 in for that. dr dt is the rate of change in my radius. That was 2. Okay, multiplying this all out, I'm going to get 120 pi. And this is a rate of change in area with respect to time. Area would be measured in meters squared. So this is meters squared per second. Okay? So this is one of the simpler examples illustrating how related rates works. So just kind of recapping on what we did. We looked in the problem for what kind of quantities are related to each other. What quantities are we actually interested in? It mentions the radius of a circle, a circular pattern, and the area of that circle. So radius and area, we want to know how those two things are related. The formula for the area of a circle is showing that relationship. We're given information about some rates of change as well. So to get those rates of change to appear in an equation, we have to differentiate both sides of this with respect to t. And you're going to see pretty much all the time, with some rare exceptions, we're almost always differentiating with respect to time, with respect to t. But once I have done that, I now have rates of change, so derivatives appearing in my answer or in my equation, and maybe some of the variables are still hanging around as well. So the r, there's still an r in there. At that point, I need to determine what part of this equation is it that I'm trying to solve for, and what other parts of that equation do I already have information that I can plug in. And that's what we did here. So let's take a look at another fairly simple example. It says the length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? So look for some keywords here regarding the dimensions of this rectangle. I see a mention of length, width, and area. So we are probably going to try to relate all three of those. And we know the area formula for a rectangle does just that. The area of a rectangle is length times width. Okay, there's other things I could talk about with regard to a rectangle. I could talk about the perimeter formula for a rectangle, for example, but that doesn't seem to have any relevance to this problem. So you're looking for keywords to figure out exactly what relationship is going to help you solve the problem. A equals length times width. So as before, we're going to want to differentiate both sides of this equation with respect to t, because there are rates of change with respect to time that are occurring here. Both the length and the width of this rectangle are growing as time passes. So I need somewhere where I can input an 8 for dl dt, because that would be the rate of change in the length of my rectangle. Similar for dw dt, the rate of change in my width. That means that I would have to differentiate both sides of this equation with respect to t. On the left-hand side, like before, I'm going to get dA dt. Now the right-hand side, remember L and W are both changing as time passes. So each of these is a function of t. What I have is a product of two functions. That means in order to take the derivative, I would need the product rule. And the product rule here would say that I need to take the derivative of the first function, which is dl dt, times the second, which is w, plus the derivative of the second function, dw dt, times the first function. So this is what the derivative would look like. Okay, now I need to figure out what information do I know and what information am I trying to find out. So I'm given a lot of quantities in this problem. It says the Length of the rectangle increases at a rate of 8 centimeters per second. Width increases at a rate of 3 centimeters per second. Both of those are rates of change, one in my length and one in my width. So that would be the dl dt and the dw dt that are showing up in this little formula down here. We're also specifically interested at what's going on at the point in time when the length of this rectangle is 20 centimeters and the width is 10. So that is length and width. That's L and W. Notice I have quantities to plug into all 4 of these unknowns on the right side of this equation. The problem is asking me to find how fast the area of the rectangle is increasing. That would be dA dt, the rate of change in my area. So it's really just a matter of plugging numbers in now. dl dt, the rate of change in my length, is 8 centimeters per second. The rate of change, the width at the point in time that we're interested in is 10. We're told that right there. Plus dw dt, according to this, the width is changing at a rate of 3 centimeters per second. And times L, length would be 20 centimeters at the instant in time that we are interested in. That is equal to 80 plus 60, or 140. And then the units, remember, this is the rate of change in area with respect to time. So lengths have been measured in centimeters. That means area is in square centimeters. Time has so far been measured in seconds. So that's going to be 140 square centimeters per second. Okay, so these two problems are fairly similar in the sense that we're looking at a geometric shape, a circle here and a rectangle in this example that's growing. And because it's growing, we have rates of change associated with that. Rates of change in our area and our radius, or our length and our width if it's the rectangle. And the fact that we get equations that have multiple derivatives appearing in them is where we get that name, related rates. Each one of these is a rate of change in some quantity with respect to time, and they are related by the equation here. Okay, let's try and move on to some slightly more challenging problems. This one I would say is just about as challenging as the others, maybe a tad more so. In this one, we are looking for the, well, let's read it. It says a snowball melts so that its surface area decreases at a rate of 1 centimeter squared per minute. Find the rate at which the diameter decreases when the diameter is 10 centimeters. So again, look for keywords that indicate what kind of quantities we want to include in our formula, in our equation. We have surface area for a sphere, so we need to recall what the formula for that is. And then we also need to find, we're also looking at the diameter of this sphere. So if you know the formula for the surface area of a sphere, it's A equals 4 pi r squared. R is the radius of that sphere. Nowhere in the statement of this problem does the word radius appear. It talks about diameter. So I need to modify this equation so that it involves the diameter instead of the radius. So I'm going to use what I know the relationship between the diameter of a sphere and its radius r. So this would be 4 pi. The radius of a circle or a sphere is half the diameter. So I could replace that r with d over 2, right? Now, if I were to actually carry out this exponent here, this would turn into d squared over 4. I have to square that 2 as well. But because I'm dividing by 4 here and I'm also multiplying by 4 here, those are going to ultimately cancel each other out. And I just get pi d squared. It almost makes you wonder why we don't use this as the formula for the surface area of a sphere. It looks simpler than 4 pi r squared, even if just by a little bit. So this is our surface area formula in terms of diameter instead of radius, which is what we wanted. So now we can differentiate both sides of this, which would give me dA dt equals 2 pi d dd dt. I know it's a little weird seeing the dd up there, but each of these d's means something different. That d stands for diameter there. So now I'm going to look at the information that I have, see if I can plug enough stuff in to solve this, and also make sure I know what it is I'm solving for. So we know that the surface area is decreasing because it's melting at a rate of 1 centimeter squared per minute. So that would be the A here, or the dA dt, I should say, because that's the rate of change in our surface area. And pay close attention to the fact that the surface area is decreasing. That means we need to interpret our rate of change as a negative value. So with that, I would plug a -1 in for dA dt. -1 equals 2 pi d. Are we told what the diameter is? Yeah, we're looking at the moment in time when the diameter is 10 centimeters. So I'm going to plug a 10 in for d. The d dt is what we're looking for. It says find the rate at which the diameter decreases when the diameter is 10 centimeters. So we don't have anything to plug in for the d dt, but that's okay because we can solve for it now. 2 pi times 10, that's equal to 20 pi. I'd be dividing both sides by 20 pi. And I get -1 over 20 pi equals dd dt. That's the thing I'm looking for. In fact, what I should do, I should include my units as well. I didn't really think about that. So my units here, it's diameter, which is measured in centimeters, it looks like. And the unit of time I'm seeing here is minutes, centimeters per minute. Okay? Again, none of these problems have been terribly involved, but that's because these are the problems that you would encounter first in like a homework set, for a section like this. They do get more complicated. So we're going to start seeing some slightly more complicated problems as we move through these examples. I have 3 more examples to show you. The next example we're going to look at involves a boat being pulled into a dock. So it says a boat is being pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it's 8 meters from the dock? So for the rest of the examples that we're going to do in this section, you're going to want to draw diagrams. You can see this is kind of a visual section. And this is where you get to laugh at my art skills. So here's our little boat. I am not artistically inclined, just so you know. Here's the boat. It's being pulled in to this dock over here, right? So we've got, those little supports for the dock, and we're told that there's this pulley. I'm going to put it up on this thing right here, and there's a rope that's attached to the bow of the boat, and it goes to the pulley like this. And we're told that the pulley is 1 meter higher than the bow of the boat. Okay, now I made my dock perfectly level with the bow of the boat. It doesn't necessarily need to be that way, and it also doesn't affect the problem if it's that way. It just makes my picture a little easier for me to draw. So notice what I've done here is I've created this right triangle. And what are the legs of this right triangle? What do they represent? What does the hypotenuse represent? Well, the hypotenuse, I'm going to call that R, because the hypotenuse is the length of rope between the boat and the pulley. This dashed line right here, I'm going to call that D. And what that stands for is the distance from the boat to the dock. Okay? So that is a relevant quantity in this problem. Now, how would I relate these quantities? Well, even before I say that, have I included in my diagram all of the quantities that are relevant to this problem? It says a boat is being pulled into a dock by a rope attached to the bow of a boat passing through a pulley on a dock that's 1 meter higher than the bow of the boat. The rope is pulled in at a rate of 1 meter per second. So the length of the rope is changing as it gets pulled in. So the rate of change that's indicated here is a rate of change in R. It says how fast is the boat approaching the dock when it's 8 meters from the dock. So that means how fast is the distance between the dock and the boat decreasing as time passes, as in this particular instant. So we're looking for dt. We're looking for the rate of change in this quantity. These are all the quantities I'm going to need to answer this question. And if you notice, we have three sides of a right triangle. Those are related by the Pythagorean theorem. So I could write this: r squared is equal to 1 squared, which is just 1, plus d squared. Okay? And then kind of anticipating what's going to come next, I should differentiate both sides of this with respect to t. So that would be 2r dr dt. Remember, we're using implicit differentiation here, so you have to remember that these little rates of change are going to pop out. Equals, the constant goes away when I differentiate it, and then I have 2d dd dt. To simplify this equation a bit, I could also divide both sides by 2 just to eliminate those 2's. I don't need them there, so doing that simplifies my work a little bit. Now, do we have enough information to solve the problem? Well, first of all, what are we looking for? Just identify that one more time. How fast is the boat approaching the dock when it's 8 meters from the dock? dd dt, that's the thing that we're looking for. So that means I need to know the quantities of the other three unknowns in this equation before I have any hope of solving that. Do we have all three of those? The rope is pulled in at a rate of 1 meter per second. That's dr dt. It would actually be negative because as the rope is pulled in, the length of the rope is shrinking, right? It's being pulled in, so it's decreasing. So I would interpret that as a -1, but that's what dr dt is equal to. And it says when the dock is 8 meters from when the boat is, oh, I have a typo there. Oh, no, I don't. How fast is the boat approaching the dock? So when it's 8 meters from the dock, that's a quantity for d. So I can plug an 8 in for d. Notice it didn't tell me what r is equal to, but that's actually okay because I can find r if I know what d is. And that's where I can go back to the original equation, which we haven't had to do yet. I can go back to the original equation and use that to solve for anything that's not told to me explicitly in the problem. So I have r squared in this particular instance, when we're 8 meters from the dock, equals 1 plus 8 squared, right? That would be 64 plus 1, or 65, so that means r is equal to root 65 in that instant. That gives me the last thing that I need to plug in there. So now let's plug everything that we have into this equation right here. R is equal to root 65, dr dt we said was equal to -1 because it's decreasing at a rate of 1 meter per second. So -1 equals d, which was 8, dd dt, which is the thing we're trying to find. And this would imply that dd dt, after dividing by 8, is equal to -root 65 over 8. It's measured in meters, we notice. Distance is measured in meters. Our unit of time here is in seconds, so that would be meters per second. Now take a second to check if that's a reasonable quantity to be getting here. I'm mostly interested in just the fact that it's negative. Are we expecting this to be negative? And yes, we are, because that means the distance between the boat and the dock is decreasing as the boat gets closer. So the negative here indicates decreasing, which is what we're expecting to see. I do have 2 more examples to do, but I'm going to save that for part 2.